So I believe last place we left off was about z-scores. We were talking about z-scores and normalizing. Kind of like similar to making things into percentage, so it's easier to read, like 50%, you know that's half of it, 100% is the whole thing. The percentages make it easy for us to think about where they stand. Z-score is another way to think about that, to think about where people stand. And so the definition of the z-score is it gives you the number of standard deviations away from the mean that you're talking about. And one of the examples that we've discussed here, I think, just kind of in passing but not in detail, was like the average heights or something like that. So if we know the average height of a person, then we can see where other people fit in this scenario by looking at their z-score. So I'm trying to look for the mean and standard deviation. But as we're taking a look at, as I'm trying to look for the mean standard deviation, what we can do is we can just take a look at these formulas, and this will give you the idea of how many standard deviations away somebody is from the mean if we're doing that measurement. So let's see. Maybe we can squeeze in an example here. Wait. Let's see if I can put it down here in the bottom. Let's say the mean height for men is, they say it's about 5'10". How many inches is that, if we're talking inches? 70? Let's say it's 70 inches, and let's make up a standard deviation. Let's just say, they say here it's about 3 inches, so I'll say 3 inches. Now, if we take a look at somebody's height, any man here want to volunteer their height? Tell me how tall you are. Wait. You're 6'3". What's your name? Brogan. Let's say Brogan is 6'3". How many inches is that? 75 inches. So the question is, where does he rank among the heights of men in general? How many standard deviations away from the mean is he? So it will be about 2 standard deviations away from the mean. So let's do the calculation here. So in our case, or in Brogan's case, this is your x value. That's your data point that we're looking at. We have our mean, and since we're talking about this from a population perspective, let's use our parameters, mu, and our standard deviation is 3. So where does he place? His z value, his z-score, is going to be x minus mu, so that's 75 minus 70 divided by 3. And calculator, I should just have a calculator ready here. 1.66? 67? So if we're rounding off to 2 decimal places, then we want to go 1.666, and then we round off to the second decimal place, and it should look like this, 1.67. So out of all the heights of men, he's about 1.5 standard deviations away from the mean. Just by looking at 1.6, I mean, technically he's 1.66 standard deviations away from the mean. So that is his comparison. So the more interesting ones are like, figure out a basketball player's height, average basketball player's height when you're going into the 7 feet range, and figure out a height of somebody who's really small, and then you can see that they're further away from the average values, from the mean. So we talked about usual and unusual values, and I think last time this slide came up, and I crossed out ordinary and put usual. So 1.67 is somewhere over here, so he's still within the realm of usual values in terms of heights. So when we talk about basketball players and we talk about other people who are shorter than that, then they would be people who are unusual in height. People that are extremely tall or extremely short in terms of as compared to everybody else. Okay? So that's our z-scores. Any questions? Okay, you guys had homework questions on that already, right? And I hope you're able to answer it. And we'll talk more about z-scores when we start studying the normal distribution, is what it's called. All right, now let's take a look at a couple of other definitions. The first quartile. You know the median, right? The median separates all the data in half. Like half of the data is bigger and half of the data is less. So the quartile separates 25%. So there's a first quartile, the second quartile. We don't usually say Q2 because we're more used to saying the median. And then there's a third quartile. So instead of Q2, we actually use because we use the median because it's exactly the same thing. It just sounds nicer, Q1, Q2, Q3 when we talk about quartiles, but really it's the median. Oops, this is a typo. This is Q3. There's actually 2 more numbers that are important in this placement, and that is Q0, which people don't use, and Q4, which also people don't use. What do you think Q0 would be? Minimum value. Minimum. So out of your whole data set, the smallest value is going to be your minimum, and your maximum value is Q4. So after having written down Q0 and Q4, we don't really use Q0 and Q4. So we just use minimum or min, maximum or max, and then we use median, MED, median. But if you want to put it all in nice order with Q's, then it's really Q0 through Q4. So this is a little bit different from the whole numbers in the z-scores when you say z is equal to 1, 2, 3, or -1, -2, -3. because that just tells you how far something away is from the mean. Here, we're actually looking at values that are separators that separate the data set. So the idea here is between these quartiles will lie your actual data. So 25% of the data goes in here. I think we need to come up with a set of data for our class for today to use. Let's take it out and put it in our calculators. So I'll ask you the same question I did last time, but this will hopefully we'll get some different answers here. I can decide to put it in L1 or L2. I think I'm just going to erase L1. That was our original set of data from last time. And remember how to erase? I move the cursor up to the L, and then I press clear, and I'll press enter. So my list is clear. All right, let's go around the room again. Let's see how many hours you guys studied between Thursday, when we left class on Thursday, and tonight. Okay, so let's be honest and try to be honest. Okay. All right, so let's start on this side. 5 hours, all right? What? One. 7. 10. 13. 6. 5. 5. 10. 3. Yeah. 4. 6. 1. 10. Yeah. 20. 4. 6. 4. 6. All right. So we got data from 19 people here, and this is how many hours you guys studied. Now, if we look at this set of data, it's hard to think about how to split this up or break this up. And then we're talking about finding the Q1, Q2, and Q3. The idea for this is maybe if we can put this in order, and there was 19 people that said something. Yeah, so 19 people. So about 4, I guess, do you remember how to find a median? In a calculator. In the what? Well, no, not yet. But the calculator is the way I'm going to eventually want you to find it. But you have to put it in order. So that's the tricky part about this, is that you have to take your data and put it in order. Now, we have 19 people that responded, so that's an odd number. And so what we're going to do is if we put it in order, we're going to take the very middle, whatever the middle is, out of 19. I think it's 10, right? The 10th person. So if this was all put in order, and then we look for the 10th person, and we can find the median. And once we find the median, we can split that up to 2 sets of data and find the quartiles. So that's how you would do it by hand. But instead of doing it that way, we're going to do it using the calculator way, since we've already punched it into our calculators. Yes?
Can you order the numbers on this?
Yes, you can. You want to see it? Okay. If you're interested in putting it in order, which might be helpful for like a quartile thing or something, or not a quartile, but a percentile. Let's put my L1 in order. So to do that, let's go to, let me clear the history here. Let's see if I remember. Let's go to second function and stat. So I'm accessing the list. And I went to the right arrow to OPS for operations. And then I see a sort A here, sort ascending order versus sort D, which is descending. So I'll select sort A. And then it goes to my home screen that says sort A parentheses. What do I want to sort? So I want to sort L1. So second function in number 1. Close the parentheses and press enter. It says done. So let's take a look at L1. So stat, edit. Now L1 is in order. So if I look for the 10th element, the 10th value, 6, that should be my median. Okay? So that's a way to sort your data set and your calculator. So it's second function, stat, and then OPS, and then L1, or sort A. L1 parentheses 10, so I'm on the 10th number. And then according to this list, I got 6. All right, now to actually do to find all the minimum, the Q1, the median, the Q3, and the maximum, we could do just the 1 var stats. So let's go to stat, calc, and then select the first one, 1 var stats. And then second function in L1, so I'm going to do 1 var stats on L1. And then I press enter. So we have the mean and the standard deviation like we've had before. You actually have the n also, the number of numbers that you've inputted. But if you scroll down, whenever you see an arrow down after you do a calculator command, that means there's more there to look at. So if you scroll down and take a look, we have those 5 numbers that we were just talking about. That's the min, x, or the minimum, Q1. Now Q2 is not written as Q2, it's the median. And then there's Q3, and then the maximum. So the minimum is 1, the maximum is 20. 4 hours is the cutoff between the first handful of people that studied that's less than 4 hours. Or let's put it this way, 25% of you studied less than 4 hours, and 75% of you studied more than 4 hours. That's what this 4 means.
That's, you can also look at Q2 and 3 or whatever on the
Yeah. So in the median, half of you studied less than 6 hours, half of you studied more than 6 hours as a group. The 10, it says 25% of you studied more than 10 hours, and 75% of you studied less than 10 hours. So that's what those numbers mean.
For the quiz, you just want us to do the picture of the plot and show how we got the Q?
Yeah. So just say you did 1 var stats, and then you did the box plot from this. So you write down the 5 number summary, and then you would draw the box plot. So in fact, let me do it. Well, let's hold on to this idea, and then the box plot comes in the next section. So I'll do it then. All right. So these are quartiles to break it up into 25% of the data set. Percentiles is the same thing, except you're breaking it up instead of 4 equal pieces for quartiles. You're looking at percentiles. You're going to break up your data into 100 little pieces. Now, our example with only 19 data points is not a very good example for a percentile. Usually, percentiles are used when you have a really, really large number of data. Having a small number of data isn't very useful. But we could still try to do the problems with our 19 data points. But basically, a percentile breaks it up into 100 or 99 pieces, where you look at P1 through P99, and then if you look at P0, that's like the minimum, and P100 would be like the maximum. And this is used more for like being able to compare yourself to the people that took the SATs with you the same year, or people that took the GREs. Usually they report the percentiles. They report your performance based on everybody else who took that test. So there's two types of problems in this percentile business. One of them is that if you have your particular score, where are you? Where do you rank? What is your percentile compared to everybody else? So this is finding a percentile given a score. Now let's take a look at doing a problem like this. Let's pick on somebody. Anybody want to volunteer? How many hours did you study? One. All right. Madison. One hour. I guess that's singular. So this is a little tricky because that's one happens to also be our minimum value. But we could see how this works out. Let's take a look at our list again. And fortunately, we actually have our list already ordered, right? So we might need to do two examples. See if it'll paste. No, it won't paste. What am I going to do? Let's do this on another sheet. So, Madison studied 1 hour. Let's find her percentile. Now, this is because 1 is the smallest number, this is probably not going to work very well. But if you look at that formula for the percentile is the number of values less than x divided by the number of total values. So if we were to use that algorithm, well, it's kind of including 1. So number of values less than 1 divided by total. So how many values are less than 1? 0. Divided by 19, which is 0. So she fell in the 0th percentile. Let's pick somebody else. Let's pick somebody who's it's okay. 4. How many? There's 3 people that studied 4 hours here. Okay, so let's pick 4. Let's pick on, what's your name? Chris. Chris studied 4 hours. So what's his percentile? Percentile is going to be given by number of values less than 4 hours. So now this is a little tricky too, because there's 3 of them that have 4 hours for what they put. So I'd probably just use the first one, because I mean we're looking for a number of values that are actually less than 4. So how many values are less than 4? There's 3 values, 3 numbers less than 4. Right? Let's make a note of that. Well, actually, this is strictly less than, so I'm not even counting any of these 4s. Yeah, 3 values are less than 4. So we got 3 in the numerator and divided by the total number, which is 19. And so let's figure out what's 3 divided by 19. 0.15. So this is about 15%, right? I wouldn't call it percent. You could say number of hours studied falls in the 15th percentile. So I would use 15th percentile, or TH here for the 15th, or 15th percentile to denote that we're actually looking at a percentile, putting Chris's number of hours that he studied in a percentile. Okay? So that's how percentiles would work. Any questions? All right. Okay, so you could have a problem where you're given a score and you're asked to find a percentile, or it can go the other way around. You could be given a problem where you're given a percentile and you might be asked what would the score be. So converting kth percentile to a corresponding data value. So maybe I can ask, what is the 60th percentile for the number of hours studied? So what I would need to do is I would need to use this formula. This formula is called the locator. Now this L that you get here is not your final answer. You actually have to locate your value. So locator gives you the position of the value. You still need to find it. Okay? So let's do an example. I'm just going to copy the formula. So let's say how many hours falls in the 60th percentile? All right, so we need the locator. So our N, our K are given. So in this case, K is equal to 60. N is equal to 19. We had 19 people. So your L is going to be 60 over 100 times 19, which is, what's that equal to? What's 0.6 times 19? 11 what? 11.4. 11.4. Oh, what do we do with a decimal like this? So some people go to 11, but if we take a look at the notation here, or the instructions, you find your locator. If your locator is a whole number, or if your locator is a whole number, no, in this case it's not a whole number, we want to round up. Round up. So this is a chart in your book somewhere that just tells you how to use your locator. And really, this chart tells you what happens if your locator is a whole number or a decimal. So in this case, we ended up with a decimal, and so we're going to round up. Even if it's 11.1, you're still going to round up to 12. Okay? So that's the rule that this book has. If you go to other places, they might tweak the rule a little bit, but let's just go with this rule. So back to our example. We're going to round up to 12. Now, your locator is 12. That's not your answer. What you need to do is you need to now go look at your sorted list and look for the 12th position. So let's take our calculator and our list. And look at my 12th position in my list, and that looks like it's a 6. Uh-oh, here's the thing where I can't move it around again. Yeah, still see. So the data point, or the value, in the 12th position is 6. So this is your final answer, 6. Okay, or 6 hours. If you remember, this happened to be the median as well. And so that's just because we have a small set of data and there's going to be overlapping and stuff like that. So and there's a lot of similar numbers too when you guys were reporting. So probably the 40th, the 50th, the 60th percentile is going to be all the same. It's all going to be equal to 6. But that's what happens when you got a small set of data. Any questions? All right. If for some reason you did your locator and you got a whole number out of that, then you're kind of looking at the number in between the two numbers. Kind of like if you have an even number and you're trying to find the median, you take the two middle numbers and then you find the mean between them. It's going to be the same business over here. Okay. All right. So, for example, in this case, if L equals a 12, so it says the kth percentile is midway between the Lth value and the next value. So, take the value, 12th number, and the next number, 13th number. Whatever they are, let's say, should I make up numbers or 6 and 6, right? Let's say 6 and 7. 6 and 7. So these are your values, and this is your position. Yeah, so it'll be the mean between them. The position is between, the position is 12. So L is equal to 12. So you take the 12th position and the 13th position, and you take those values and take the mean of those two values. And so it's going to be 6.5 hours. Okay? Okay, let's move on to just a couple more pieces of statistics. The interquartile range, it's like the range, right? It's finding the range of things, but instead of finding the range from the maximum to the minimum, or minimum to the maximum, the interquartile range goes from Q1 to Q3. It just finds the range of values from Q1 to Q3. So I didn't really stress this too much, and I don't really stress this too much in the class. But in a lot of statistics that you might be reading in the future, you guys will be reading some statistics in the future. And especially if you're going to go into like sociology or something, psychology and sociology type studies that you might have to read. They talk about IQR a lot, and that's the interquartile range. And so that this becomes an important value for us because it kind of helps define outliers, things that are too far off from the bulk of the data. So that's the interquartile range. It's really just the difference between the Q1 and Q3. The semi-interquartile range is kind of like the difference divided by 2. It takes a look at the length of the quartile and it cuts it in half. So that's used even less, and then the mid-quartile is used also even less than the IQR. So out of these three, I think the IQR is the most important. But there are formulas that are available. Okay? All right. This one, I don't know I've never seen this before used, but it's the 10 to 90 percentile. Yeah. Okay. So let's move on, and after just talking about the quartile, the other important part, which is in your quiz, is the box plot. So let's take a look at the box plot. So other statistical tools, graphs and measures of center, measures of variation to investigate in order to understand some of the characteristics. Exploratory data analysis, they call it. And really, out of this whole section, the most important tool to get out of this is the box plot and being able to read box plots. There are other things that they show in this section that you can take a look at. Here's where they finally define an outlier. An outlier is a value that's located very far away from the rest of the data set. Kind of makes sense, right? An outlier. And if we kind of look at our data, there's somebody who studied 20 hours. What's the next number right before 20? Do you remember? 13? Somebody studied 13 hours, and then there was a big jump to 20. So we might take a look at 20 as something that's really far away from the rest of the data. So that might be considered an outlier. So outliers in statistics, they really want to be careful when they're doing a study. They want to be careful about how to treat an outlier, because an outlier can really, you know how the CEO from a company got a raise and then that changed their mean a great deal. Outlier has an effect on the mean and on the standard deviation, because both the mean and standard deviation takes all the numbers into account. So if you have one value that's way out there, it can mess up your data. So it's important to determine whether that outlier is really an integral part of your data set, or if it's something that maybe you can sweep under the rug and say, we'll do another set of statistics without the outlier just to see this one person or this one data point can really mess up the rest of the data. So maybe there's something else happening with that outlier that made it have such a high value. So that's the idea behind knowing what an outlier is, and then it's up to you as a statistician doing your own study whether to include that. I would say it's kind of a relative term. There's a definition that's not given in the book that people sometimes use, and I don't know off the top of my head, but it's something to do with the IQR. If you determine your IQR and then you add another quartile to it or something like that, and if it's way past beyond that, then it might be considered an outlier. All right. So the 5-number summary, the min, the Q1, the median, the Q3, and then the maximum are 5 numbers that give an important description or a visual of how the data set might look like. And we use the box plot to kind of get a visual of this thing. So the box plot is, they call it box and whisker because the other side looks like it might have a whisker to it. But we'll go back to that example, the short example that we have. So let me just draw how it might look like. You would draw a number line with the max and min. And then you would draw a box with a Q1 and Q3, and then in the middle of the box somewhere you would draw the median. So this is how the 5 numbers come up in this box plot. Now, regardless of what your numbers are, if you write your box plot the same every time, if you draw your box plot the same every time with the same length, then it's not going to be that effective. What is effective is to see how long the distance is between Q3 and the maximum, for example, or where the median lies. Is the median closer to Q3 or is it closer to Q1 or something like that? So the shape of the box plot does actually make a difference and could help describe the shape of your data set. So let's do our box plot. And let's first use the calculator to do our box plot. So I think you guys have done your histograms. We've done our histograms in the calculator. And if you remember where that was in our L1 or the P1 or plot or whatever. So let's go to second function and plot, or the y equals to the stat plot. It turns out that you can do a histogram and a box plot at the same time because we're looking at the same number range here. So let's do that. Let's keep the histogram and the box plot the same. Or let's keep the histogram there. I'm going to go to plot 2 and turn this one on. I don't know if I should do that. Should I just... What you can do is you can go to plot 1 and not have the histogram and have only the box plot. Now I'm just confusing you. So I'm going to go to plot number 2, and I'll turn this plot on. And then when they ask me for the type of graph, I can't use the down arrow to get there. I have to keep using the right arrow. Because if I use a down arrow, I'm going to go to X list. So I'm going to select the box plot that has a stripe in the middle. That's going to give you a 5-number summary. So I'll press enter. And then I have my X list and my frequency. Okay. So since the last time, our range probably changed. So I want to adjust this according to the window that I have. And I know that the smallest number is 1 and the largest number is 20. But in some cases, especially when you're doing the box plot, you can let the calculator figure things out for you. So I'm going to go to zoom. Let's try that again. Zoom? No. Are you guys getting something different from what I'm getting? Yeah, I'm still not used to this TI-84 business. All right. So when you press zoom, you get something like this. Zoom in memory. What?
I was getting what you were getting.
Okay, so if you're getting what I was getting, what I did is second function and quit. so I can get out of that mode. And now I'm back to my home screen, and I'm just going to press zoom and look for zoom stat. I think zoom stat is number 9 for even the TI-83 for most calculators. So if you have that memorized and you do this over and over again, you'll just go press number 9 when you hit zoom. Just press number 9 and you're there. And what this will do is this will automatically figure out a good window for your statistics values. So I have a histogram here. If you didn't do a histogram, that's fine. We don't need a histogram for this problem. But there's my box plot. Should I get rid of the histogram? Is it bothering you?
I'm staying.
Error?
So when you're under bar stats,
Oh no, we didn't do one var stats. We just have your.
because you show the big
Oh yeah, that was just my home screen. That was my last home screen. I didn't do on var stats. So, all right, just get rid of the error and press zoom and zoom stats and see what happened. Zoom, I look for zoom stat, and I just use the arrow key to look for zoom stat. All right. Let's do this again. Let's go to second function and stat plot. Let me just do it a slightly different way. I'm going to turn all my plots off right now. So I'm going to press 4, and I'll press enter. So all my plots are off. When I go back to second function and stat plot, I see that all my plots are off. So I'm just going to select one, the first one. So I'm going to hit 1, or you can just press enter. And I'll turn this one on, so I'll hit enter. Arrow down to the type, and then I have to use my right arrow to go to the box plot. And it looks like there's 2 box plots. One of them has a line in the middle. That's what I want. I want the one with the line in the middle. Okay? So I'll press enter. So now that's selected. And then I just arrow down. My X list is an L1. My frequency is going to be 1. Oh, that means your type is not you didn't select the box plot. So the type has to be the box plot, which is the one in the middle bottom. Did you hit enter? And are you getting that thing? Is it graphing already?
No.
No, hey, can I see? There's some chords in the Uh-oh. Okay. All right, so let's say you're on that screen. All right, so second function and quit to go back to the home screen, and then this is where we go to zoom. So hit zoom and look for zoom stat. And then when you press enter, you should get this. Yeah?
So when we press zoom, you want zoom stat?
Yeah. Zoom stat. Looks like I have a graph of something over here that's not that important. In the middle. So remember the choices for if you go back to stat plot, there's two boxes. One of them is this box that's blinking right now, and then this is the other box. And you want to make sure you have that one. That one has a line in the middle. All right. Now, if you look at the shape of that graph, you'll see that the median is a little closer to the Q1, and then between Q3 and the maximum, there's that long line. So that's important to view so that we can kind of get an idea of how the graph might look like, how the histogram might look like, without having to draw the histogram. Okay, so we're not drawing the histogram. So it turns out when the numbers are bunched up like this, like in the Q1, the minimum, the Q1 and the median, they're kind of more together than the Q3 and then the maximum. So it looks like most of the data might be bunched up on the left side, which means this is skewed to it'd probably be skewed to the right. So if we were to draw a histogram, we'll probably see something skewed to the right. So that's important to be able to tell from the box plot. The other thing that's important with the box plot is if you take a look at the box plot in the slide here, they actually put the numbers that are associated with a 5-number summary. The minimum, the Q1, the median, the Q3, and the maximum. So they put these numbers here as labels for the box plot. So you could do that too. And in case you don't know, or in case you didn't write down the 5-number summary, while you have the box plot up like this, you can go to Trace. Make sure you're on the P, the appropriate P. So if you had the histogram and did a box plot, then you're probably looking at P2. I'm looking at P1 because I only have one statistics plot here. So P1 colon L1 is what they would have. And if I use my left and right arrows, and if you look at those values down in the bottom, they give you the min, the Q1, the median, the Q3, and then the maximum. Those are the 5 numbers that I want you to include in your box plot. So there are several ways for you to draw the box plot. Let's say this is what you see in your calculator. So in the test situation, what I would do is I would probably want to draw a number line. This isn't the box plot yet, this is just the number line. But I would draw the actual box plot up here. And then it looks like 10 is going to be my Q3. Do you remember what Q1 was? Can you guys trace your box plot? Q1 was 4, so 5, 4. So 4 is somewhere over here. And then 6, 5, 6. And then if you labeled it down in the number line in the bottom, then that probably would work. If you didn't label it, or if you don't have the number line in the bottom, then you would label it up here. 1, 4, 6, 10, and 20. So that's how you would draw your box plot by hand. But you have to try to be consistent with trying to draw it to scale. So if you got this problem, and this is the box plot you're supposed to draw, and then you just ended up drawing something like this, that's not going to be helpful in trying to view your data set, because it doesn't tell me that there's this big gap between Q3 and the maximum. So it is important to try to draw it as much to scale as possible. You know, I didn't have to use a ruler for this, but I know between 1 and 20, the middle is 10, and so that helped me figure out, you know, that there's a longer length between Q3 and the maximum. Okay? All right, so the PowerPoint has a few other good examples of box plots. With respect to the actual distribution. So here's an example of a distribution that's pretty bell-shaped. So what kinds of things do you notice in the box plot? It's pretty even, kind of. I say it's even here, but it's got a long tail for the max and the minimum. Okay? So this, if you see the Q1, the median, and the Q3 about looking pretty even, and then you see this big long lines for the things to go in the minimum and the maximum values, then you can probably say that that's a bell-shaped curve. If it was all pretty even, now this isn't exactly even, this isn't exactly in the middle, but that's probably okay. But in this case, the minimum, the Q1, the median, the Q3, and then the maximum are fairly even, then I would probably say this is what's called a uniform distribution, that it's all about the same. So there's a little bit of a difference between a normal distribution, where the bulk of the data happens between Q1 and Q3, and then all these other pieces of data go farther away, versus something that's more uniform, where it's kind of, it doesn't look even, but it's in the big picture of things, it's fairly even. And then something that's skewed, in this case it's skewed to the right, and here they start putting dots here because they start thinking about this as outliers, but I would probably continue drawing a straight line here. So box plot where the bulk of the data, you know, falls towards the minimum or towards the maximum, and then there's this long line going to the other extreme, then that would be skewed. In this case, the tail, or the longer part of your box plot, is happening on the right side, so this is skewed to the right. Okay, so that's how you can use your box plots to kind of tell what's happening with the original data set. And that's why it's important to draw your box plots as much to scale as possible, so you can do some comparisons of the data points. Okay? So A is a normal distribution. The Q1, the median, and Q3 are kind of bunched together, and then long tails on the left and on the right. Uniform distribution is fairly even all the way across, and then skewed is one of them. The box is closer to one side, and then there's a long tail on the other side. Yeah?
On the test, do you expect us to know how to calculate stuff without the calculator, or?
You can have the calculator with you. It'd be nice if you can do it without the calculator, but actually I would suggest that you do the calculator for things.
How would we show like
Tell me what calculator command you use. So I don't expect you, to find a standard deviation. You don't have to write the formula, but you just say 1 var stats, and this is what I got. Okay? So box plots are also good for being able to compare data really quickly. It turns out that, I'll skip over the modified. It turns out that because box plots, you're really looking at just 5 numbers. It turns out that this is easier to construct than say, like a histogram or something. Where a histogram, you have to include all the data, you have to put them in little bins, and then you have to figure out how high each of those values are. So with a box plot, you just take 5 numbers, you put them into a computer, and then you'll have a box plot. So it's good. Turns out that it's a good way to compare 2 different data sets if you're comparing 2 different populations. Like in this case, male and female for pulse rates. I saw another box plot that compared the sodium in hot dogs, where you have a beef, a chicken, and pork, and miscellaneous, whatever that means. So then you're able to compare 4 different box plots at the same time to try to figure out how they compare. So box plots are another quick, easy way to compare things, and you'll see it quite a bit in a lot of statistical studies that compare things. Question? Yeah, you can construct a box plot for each. Yeah. And most box plots that you see, a lot of, our calculator would put the box plots like this in horizontal order, but most box plots are actually done vertically for comparing. Yeah. Oh, Google's, yeah, if you search box plots, you'll see a lot of the box plots are vertical. But you could just turn your head sideways and it'll work out. All right, turn the computer sideways. Okay, so I think that was the last slide for this section. So we're going to be on to Chapter 4 now, which seems to it takes a turn in terms of what we're doing. We're doing all this statistics and doing all these number calculations, and all of a sudden they throw in this subject called probability. So I think I already mentioned that probability is our bridge from descriptive statistics to what we're calling inferential statistics. And so this is going to be an important part of our study. Actually, Chapter 4, 5, and 6 will help us bridge the 2 things. And so that's why I was figuring Chapter 6 would be a good place to cut the semester in half, so that we've done descriptive statistics, and then we're doing probability and distributions. And after the midterm, we'll be ready to jump into inferential statistics. Now, this has a lot of important information, but I think just for the sake of time, we're only going to cover 4 sections here. I think I might have 5 in the homework as well. But counting is definitely a fun subject that you can do in statistics, but we just don't have any time. So counting is an exercise where you can do stuff like try to figure out how many ways you can get, how many different 5-hand cards there are in poker. Turns out there's like over 2 million ways to get a 5-hand card in poker. So, and then from there you can construct probabilities. So for us, we're just going to focus on the first 5 sections here and eliminate the 6th section. And we're going to talk about the basic rules for probability and a couple of rules of addition and multiplication, and then complements and stuff like that. Now, there's a statement over here called the rare event rule for inferential statistics. This might make a lot more sense when we look at it again when we in our study of inferential statistics in Chapter 7. But it's mentioned here anyway, so let's see if we can make sense out of it. If under a given assumption a probability of a particular observed event is extremely small, we can possibly conclude that the assumption is probably not correct. So this is a rare event rule. So like I said, this will make a lot more sense when we put it in the context of inferential statistics when we're testing things. And, you know, phrases like extremely small, what does that mean? We're actually going to try to quantify that in inferential statistics. And there's a good example that they have in the PowerPoint slides when we get to Chapter 7, something about pregnancy, enforcing the pregnancy to have a girl versus a boy. Have you guys heard of that? There's this company, I don't know, maybe it's made up. There's this company you go to, and then you say you really want to have a girl for your baby, and you're newly pregnant, and they give you a package where they try to change your diet and change your activities to try to coerce your baby to be a girl. I don't know. Maybe there's something not right about that. Anyways, we'll take a look at that when we get there. So, probability, the idea of probability. The section introduces basic probability concepts and how for us to look at a particular probability and then be able to interpret the value that we get for the probability and what it actually means. So, some basic definitions of probability. An event is a collection of results or outcomes of a procedure. I don't know, maybe they should have defined simple event first, but a simple event is an outcome that cannot be broken down into any simpler components, they call it. So we're going to be basically focused on simple events. And a sample space is a collection of all possible simple events. And what's important about the sample space is for us to be able to figure out what is the size of our sample space. Because the size of the sample space will give us our base, will essentially be our denominator for finding probability. So, simple example, flipping a coin, you either get a heads or a tails. Heads and tails are simple events. And your sample space would be the collection of all simple events, the head or the tail. So you have two elements in your sample space, and the two events are heads or tails. Okay? I think when we get to rolling dice, that becomes these definitions might pop out a little bit more. Notation. We use a capital P to denote a probability. We normally use the first few letters of the alphabet, or sometimes we use E, which is still kind of considered the first few letters of the alphabet, to describe our event. Or sometimes we use a phrase or a number that would make sense for us. But more importantly than denoting your event, P of something is a probability that your particular event will occur. So, in our example of tossing a coin, your sample space is, I have a curly brackets for the sample space because it's usually denoted by a set. My sample space would be H in a T. So instead of saying, let's say the event that I get a heads is A, instead of saying that, why don't I just say H for the event that I get a heads? Or T would be the event that I toss a coin and I get a tails. And so the probability of getting a heads will be denoted by P parentheses H. And you guys know what this is, right? That's the probability of getting a heads. It's a half. We'll see why, because there's one simple event that gives you a heads, and there's two events in a sample space. So that's 1 divided by 2. And we'll get to that when we actually formally define our probability. So, I had a bunch of high school kids early this morning. I'm doing some special program called the STEM Institute. And today we did exercise on rolling dice. So what they did was they rolled 2 dice, and each of them rolled it about 50 times or 75 times, almost 100. And they wrote down their answers and they tallied it up. And so based on their rolling the dice and then tallying up all that information, what we've found was the probability for rolling each of those numbers that you would get from the dice. So this probability, this is called the relative frequency approximation, and this is based on conducting your experiment a whole bunch of times. And based on conducting your experiment a whole bunch of times, we can define a probability for an event happening. So we could do this like we could toss a coin. We could toss, let's say we toss a coin 1,000 times, right? And let's say about 530 times we got heads. So we can say the probability of getting a heads would be 530 out of 1,000. And that would be our relative frequency approximation, because it's based on an experiment that we did, and we're getting the results that way. Okay?
You want to simplify?
Not necessarily. So we'll talk about how to round off your probabilities a little bit later on. So a relative frequency approximation of probability is based on doing this experiment a whole bunch of times. Now, there's another one called the classical approach to probability, where instead of doing the experiment a whole bunch of times, if you know more information about the scenario, then you can actually figure out the exact probability. So in terms of tossing the coin, since that's a really simple example, so let's say we toss the coin 1,000 times and we got 530 heads. Then we can say the probability for getting a heads is 530 out of 1,000 for our first rule, rule number 1, the relative frequency approach. But now, if I look at the classical approach, I know there's 2 different outcomes for getting a heads. Or there's 2 different outcomes for tossing a coin, a heads or a tail. And there's one way to get a heads, and there's 2 possible outcomes for your experiment. So the probability for getting a heads is 1 out of 2. So what's the difference between the 2 of them? Yeah, so if it was die, it would be 1 over 6, and then it would be something different. Well, anyways, this rule 1, the relative frequency approximation, and rule 2, they call it, the classical approach, they have a connection between them. When we toss a coin 1,000 times and we got 530 heads, we didn't get exactly 1/2. 530 is like 0.53. It's not 0.5, period. It's 0.53. So it's a little bit different. But this idea of the law of large numbers says that if you repeat your procedure many, many, many more times, then you'll eventually start looking like the actual or the classical probability. So in terms of calculus, it would be like limits. Let's not talk about calculus. In terms of what we were talking about, so maybe if we toss the coin 3 times or 10 times, so say we toss the coin 10 times, we got 7 heads. Then we can say the probability for getting a heads is 7 out of 10, or 0.7. Say we toss the coin 100 times, and I'm just going to make up a number here. Let's say we got 64 heads. Then the probability of getting a heads would be 64 out of 100. And let's say we toss the coin 1,000 times, and we got 530 heads. Then the probability of getting a heads is 530 divided by 1,000. Yes. The more times you do this, if you do this 1,000,000 times, you're probably going to be pretty, if not pretty damn close to 0.5. If not exactly 0.5, then it's really, really close to 0.5. So here we got 0.7. Here we got 0.64. Here we got 0.53. You're getting closer and closer to the actual probability. Which is the classical probability, yes. So the actual probability is 1/2. Probability of getting a heads is 1/2. And the more times you do this experiment, the closer it's going to be to 1/2. So that's the law of large numbers. Large numbers refers to the number of times you do your experiment.
Probably why it's a really big population and sample sizes when you do a study.
Say it again?
Is that why it's good to have a
Yes.
larger group of people in your study?
Yes, that's why it's good to have, the larger your sample is, the more exact, the more precise you're going to be, the more representative it is of your population.
Is there like a gold standard for what that percentage should be of the population?
No, because sometimes your population for Cañada College is like 6,000, and if you're looking at the population for the whole state, that's really big, and so it's hard to give a number or even a percentage for that matter. All right, so there's also this rule 3 that they mention in the book called subjective probability, and this is not something that we're going to be dealing with, but just to give you an example of what this means, if you go to Vegas and you know the odds for the USA making the finals in the World Cup, versus the odds for Brazil making the finals for the World Cup. You know, those are all based on knowledge of the teams, the game, the players, and things like that. And so that's what they mean by subjective probability. There's some special knowledge that needs to be known there. And then they do the calculations not really based on numbers, but they kind of base it on ideas and skill level, which sometimes is pretty hard to quantify. So, kind of, yeah, take a practice test. I also look at this as it's kind of subjective based on the information that's not common knowledge to people, or something that's that's more difficult to quantify. What? Ability to count cards, yeah. So something like that. Okay, it's 8 o'clock, so this is our break time. We'll come back, we'll talk about some properties for probabilities, like limits and stuff like that, and then we'll see how far we can get in this chapter.